You're able to hear me, right? Anyone can reply.
Yes, ma'am.
Okay, fine. You're all able to hear me. Okay, fine. Now let's go into the session. Okay. Yeah. You're able to see my screen?
Yes, ma'am.
Okay. Okay. Fine. Let's start. So, as usual, we'll go with the brief recap of lectures of this week 4. Okay. So, this week 4 content was based on polymeric materials of different kind, right?
Yes, ma'am.
Yeah. So, the lecture 23 was on glass transition. It was, in continuation of the glass transition from the previous week, right? So, here this week you went through relaxation process, right? Where you came across segmental relaxation instant, where in segmental relaxation again you went through this instantaneous relaxation, no relaxation, and then activated process, cooperative process. So activated process had equation similar to that of a, what kind of equation it had? Someone remembers? Someone remembers? Are you there? I just request you to speak or type in the chat box, because I'll not be able to see whether you're there or not when I'm in the presentation mode. Okay, there is nothing right and wrong. Okay, anyway, I'll just say, so activated process had a equation similar to that of the Arrhenius equation, right?
Yes, ma'am.
Yes, and then there was a discussion on the free volume theory, and then WLF equation and Vogel-Fulcher equation, and then Arrhenius and WLF dependence was also discussed, and there was a discussion on other type of transitions also, right?
Yes, ma'am.
Okay. Okay, and then lecture 24 was on sustainability. It was on states and environment, where there was a discussion on global and long term impact. So there was a discussion on plastics everywhere, right? Though we saw that the production of your PET, I guess, right? It is comparatively less to that of your cellulose, but when it comes to overall impact, that plays a vital role in really playing, you know what kind of role does the polymer play in the environment, right? And what kind of impact on the environment, right? And there was a discussion on the biogeochemical cycle, where what is the role of the polymer, whether they are going through the entire cycle, or they are just a part of the cycle and then they come off. So if they are just a part of the cycle and then come off, there's really no sustainability in the picture. So the ultimate aim is to bring in the polymer, the synthetic polymers also, into the biogeochemical cycles, right?
Yes, ma'am.
Yeah, yeah. And then there was a discussion on different type of biogeochemical cycles like carbon, nitrogen, right? Water cycle and all. And then nitrogen cycle was discussed in detail with industrial chemicals as well, and then from nature as well. Okay, and then states in environment. How about plastics? In environment, like in water, what are the forms it is there? Can you say what are the forms it is there in water? Someone remembers?
Macroplastic, microplastic, and dissolved.
Yes.
Uh, and it's less denser than water, so it can be transmitted to long distance.
Okay. Okay. That's good. Good.
And in soil, it will be macromolecule and micromolecule.
Yeah. My macro and microplastics. Similarly, in case of air, it is microplastics, right?
Yes, ma'am.
Yeah. Yes. This was about the lecture 24. Lecture 25 was on liquid crystalline polymers, right?
Yes, ma'am.
Yes. And then an introduction was given to liquid crystals, right?
Yes, ma'am.
So, what is liquid crystals? They
The
have,
segmental motion will be liquid like, ma'am.
okay,
And its arrangement like in crystal.
yeah. So, they will have some kind of an arrangement which is solid like, as well as some kind of flexibility and motion, which is liquid like, right? So that is what is about the liquid crystalline polymer. And then what is the free energy change in case of liquid crystalline polymer? There was a discussion on liquid crystalline polyesters, and then PET versus liquid crystalline polymer was discussed, and then aramid Kevlar was discussed, right? Yeah. And then lecture 26 was on copolymers. So it was basically concepts of copolymers, where the homopolymer and copolymer concepts were introduced, right? And then different sequence of distribution was introduced, right? Someone can say what kind of different sequence of distribution copolymers might have.
Random alternating block copolymer, graph
Yes.
copolymer,
Yes.
and gradual copolymer, I think. And that
Okay.
is not in lecture.
Okay. Okay. It's actually gradient copolymer.
Yes, ma'am.
Yeah. And then how can polyethylene be a copolymer, right? There was a discussion on that as well. Even though it is a CH2 link, again that it can form a copolymer, right?
Yes, ma'am.
And then there was a discussion on silicone polyether, which is a very good surfactant, having multiple different type of applications in various fields, right? And then there was a discussion on chitosan and chitin also, right? Where a small unit change, it converts the it changes the property also, right? Okay. And then lecture 27, it was on properties of copolymers. So how control polymerization for getting a specific copolymer, where this reaction rates and all was discussed, right? R1 equal to K double 1 by K12. You remember different regimes of reactivity ratios, right?
Ma'am.
Yeah. And then copolymers that are related to homopolymers. And then what are copolymers which are related to homopolymers? So they will have kind of an additive behavior, where the mixing laws and all will suit, right? Your random or alternating copolymers, whereas in block and graph copolymers, the properties are very similar. The mixing properties are all very similar to that of blends, right? The
Yes,
combination
ma'am.
properties assessments. Yeah. Okay. Next. Next, the lecture 28 was on blends. It was on concepts again. So where blends mixtures of polymers, that are mixtures of polymers. So you can either form by mild blending, solution blending, reactive blending, right? And then miscibility in polymeric system was discussed, right? And mixtures of A and B was discussed. And then polymer solvent miscibility was also discussed. And then the final lecture of the week, it's blends 2 actually, properties. So Gibbs free energy change due to mixing was discussed, where first it started with the ideal gas state, ideal gas explanation, and then it was brought into the polymeric applications, where the Fleury-Huggins theory for mixing of polymers was discussed, right? And then polymer blends and phase separation, a critical temperature, and then TG of miscible polymer blends was discussed, right? Where Fleury-Fox equation was discussed. This Fleury-Fox equation, we used it last week, right? Do you remember? We solved a problem. Hello, is anyone there?
Yes, ma'am.
Yeah. Shweta and Somima, you can also answer. There is nothing right and wrong. I think Shweta is having some, background issue, I guess. She can type in. Somima, you can open up and speak. Okay? You can open up and speak. There is nothing right and wrong. Even if it is wrong, it's fine. End of the day, I'm going to explain. Okay? Feel free to answer. Okay? Okay. Now, can we start with the assignment session? Okay. Now, you are all going to answer. Question number 1. Perfect energy storage corresponds to lambda tends to 0, no relaxation. Lambda tends to infinity, instantaneous relaxation. Or lambda tends to 0, instantaneous relaxation. Or lambda tends to infinity, no relaxation. What does perfect energy storage corresponds to? Uh, Shweta, I'm not able to hear you properly. You can just type in. You can just. Can you type in your chat box, because there are a lot of noise in your in your side, actually maybe some issues there. Can you just type in the chat box, ma? So in the meantime, someone else can also attempt. What does a perfect energy storage corresponds to?
Ma'am, lambda equal to infinity, ma'am. No
Okay.
relaxation.
Huh?
No relaxation.
Okay.
Option D.
Option D. So Swamima, do you agree? Swamima, are you there? Are you able to hear me?
Yes, ma'am.
Okay. Do you agree with this answer? Is it lambda tends to infinity and no relaxation? What is
Lambda tends to infinity, no relaxation. Yes,
okay? What is
I.
lambda? What is lambda? Both of you can answer. All three of you can answer. Of course, Shweta can type in. Someone wants to say?
Relaxation time.
Yes, yes, you're right. So, lambda tends to infinity, no relaxation. That means perfect energy storage. When lambda tends to 0 means there is an instantaneous relaxation. That means complete dissipation. So, relaxation time says on your dissipation also. How, whether it is an energy storing or energy dissipating system, right? Yeah. Okay. Now, let's go to question number 2. Free volume reaches a lower threshold leading to cessation of segmental mobility in rubbery state. Is it true or false? I think someone else joined. Sandhya. Sandhya, you're joining for the first time, is it?
Yes, ma'am. First time.
Okay, 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 fine. So, okay. Uh, so, some of you can answer this question. Free volume reaches a lower threshold leading to cessation of segmental mobility in rubbery state. Is it true or is it false?
It's true, ma'am.
Is it true?
Yes, ma'am. If there is no free volume, then the segmental mobility will be
Yes.
There is no.
If free volume is very low, then there is no segmental mobility. That till that it is fine. But under what condition? I've almost told you the answer. Someone else?
Glass transition.
Yes, it is not in rubbery state. Rubbery state, you have a good segmental mobility, right?
Yes, ma'am.
So at glass transition only, your free volume will reach a lower threshold, right? It becomes Fg. F is equal to Fg, right?
Yes, ma'am.
Yeah. Okay. Now let's go to question number 3. Alignment of molecules within liquid crystalline order for liquid crystalline polymer leads to reduction in dash but retaining dash. So does it lead to reduction in translation entropy and retains the orientational entropy, or does it leads to a reduction in orientational entropy but retains orientational enthalpy, or does it leads to reduction in translational entropy and retains orientational enthalpy, or does it leads to reduction in orientational entropy and retains translational entropy? Which one is right? I want someone else to try. See, feel free to answer. There is nothing right and wrong. If you're wrong, I'll be correcting you and I'll be helping you out. That is the ultimate purpose of this session. So unless and until, you start answering and say something, you do not know. Right? Someone, liquid crystalline polymer. Just now we had a brief recap. We said it is having arrangement similar like a solid, whereas movement like a liquid. So I've given you a hint. Now find out. Hello, are you all there? Someone wants to, you can say at least one of those 4 options which was mentioned, right?
Ma'am, B, orientational entropy, orientational enthalpy.
Why are you saying so? You have to justify the answer also when you say something.
Ma'am, option D.
Option
D.
D. Okay, why are you saying so?
Ma'am, it stay the orientation in it, it can changes, ma'am.
Okay.
So transitional entropy will retain.
Okay. Okay. But how are
Uh,
you saying that?
yes, ma'am. It can change the position in itself, ma'am, but it doesn't move.
Connect it to the name of the liquid crystalline polymer structure or the name liquid crystalline polymer. Someone else wants to make an attempt? I'll say you one more thing. Whatever Udaya said, he's right. The option D is the correct answer. So orientational entropy is reduced, whereas translational entropy is retained. No? Okay, let me say why. See, when there is an orientation of molecules, right, in case of, even in case of a polymer or any material, so your, the degree of freedom or the entropy to change to different kind of arrangements or alignments, it gets reduced, right, when there is a particular orientation, right? Say for example, in case of a FCC crystal, you all know the crystallographic arrangements, right? Face center cubic, body center cubic, and all. So if there is a particular arrangement, so in case of a face centered, for example, in every phase there will be a molecule, right? So that molecule cannot go on get placed on an edge center, right? So in that way, their orientation, is restricted, right? Once they are oriented, correct? Are you all there? Similarly, in case
Yes.
of liquid crystals also, there are certain arrangements, and within the arrangements, see, for example, even in case of, for example, in case of face centered also, let's have say a face centered also. So from this phase to the other phase, the molecule can, swap or anything, or do anything, but it cannot move to an edge center. The same case for a liquid crystalline polymer as well. So the liquid crystals, they can swap within their positions, okay, but overall they cannot change. So there is a entropic restriction. So there is a reduction in their orientational entropy, whereas still they can move in that position. They have their translation and movement and rotation, all those things possible in that particular position. That's why translation entropy is retained. That is what this translation entropy determines their liquid-like behavior, whereas orientational entropy determines their solid-like behavior. That is why they are called as liquid crystalline polymers, right? Clear?
Ma'am.
You're clear, right? All of you? Okay, I guess so. Okay. Long distance transport of plastics and water is possible due to, I think one of you told the answer also during the recap. Long distance transport of plastics in water is possible due to
Lower density.
lower density. Yes.
It flows in water.
Okay. There is one more, specific term.
Hydrogen bonding.
No, 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 no. You don't go too much into that.
Its density is similar, water
Yes,
density.
yes. It is just similar to that of water. Similarity, it's very similar in density to that of water. So that makes them, get transported. Okay. Okay. Overall impact of polymer is assessed based on how is overall impact of polymer assessed? Is it assessed only based on its production or something?
Processing parameters.
Okay. What else? What else? What else? We just went through in the recap. One more hint.
Structure.
Uh, no. This is on environmental assessment. This is from your second lecture of this week. What did what was the discussion in second lecture? Someone remembers?
It is degradation.
Only degradation?
Mass transfer exchange of small molecules to the environment.
Okay. So how do you put it in complete terms? Those overall impact. So mass transfer of small molecules and then production process. What else?
Recycling.
Recycling. So how do you put all these things in one single term?
Life cycle.
Yes, yes. Life cycle. Life cycle assessment. Okay. And then again we all there was a discussion in the lecture and we now discussed in the recap also biogeochemical analysis. Right? The sustainability becomes uh, really saying sustainable only if you could see a complete cycle passing of the polymers, right? Otherwise if it goes to a particular path of the cycle and then comes out, then there is no use. So it has to go through the if it starts going through the complete cycle, that will make it more sustainable, right? Someone else has joined. Okay. And then of course the ecosystem analysis. So these three type of assessments can be used for analyzing the overall impact of the polymers, right? So life cycle assessment, it does not mean only the production processing alone, but how is it used, and then after use how it goes, okay, how is it recycled, and at the end of its workable life, how is it discarded, everything is considered in life cycle assessment. Okay, are you all clear? Okay, now let's go to question number 6. So identify and match the copolymers. There are certain pictures given, so identify if which is a gradient, which is periodic, which is graft, and which is aperiodic copolymer.
A is graft, ma'am.
Okay, I'm still not saying you're right or wrong. I want others also to answer. What about B? A is grafted. Does everyone agree with that? I think someone called Raja Sharma, he has joined. Are you joining for the first time, Raja?
Yes, ma'am.
Okay, okay. So have you gone through the lectures? Okay, anyway, someone can also attempt. So what about B? What type of copolymer is it?
Aperiodic.
Aperiodic, okay.
And
C,
periodic D will be gradient.
okay. Now say why are you saying so? I'm not saying you are right or wrong, but you have to justify why you are saying A is a graft, B is aperiodic, C is periodic, and then D is gradient.
Ma'am, in A the backbone is one type of monomer and the branching is another type of monomer.
Okay.
And in B, there is no periodic arrangement of monomer.
Okay.
And in C, there is a periodic arrangement, ma'am.
How do you say there is a periodic arrangement?
Uh, the monomer A is 2 and monomer B is 1, like that 2, 1, 2, 1 periodically arranged. We
Okay.
can guess what upcoming monomer will be.
Okay.
And in D, there is gradual increase of monomer B and gradual decrease in monomer A.
Okay. So does everyone agree with that? Raja, Sumima, Sandhya, Shweta, you
Ma'am,
all
D,
agree?
D will be 1, no?
D, yeah. D is 1. You mean to say, yeah, okay. D is gradient, okay. That is what Uday also told, okay. What about the rest? You agree with him, whatever he said?
Yes, ma'am.
Okay. Okay. So whatever you said, you are right, Udaya. So as you said, A, the backbone is one type of polymer, and in that backbone, another type of polymer is grafted onto it. Okay. And B, it is a aperiodic polymer. Okay. There are some blocks of A and B, but this periodicity, the periodicity of A and B is not very regular, right? Because first there is one A and three B followed by one A and one B. Okay, so there is no periodicity. Whereas in case of C, as you said, there is a periodicity, that is 2 1 2 1 2 1, it goes on. And D, as you said, it is a gradient. So there is a decreasing gradient of A and increasing gradient of B. Okay, and you can also see the images of alternating copolymer and block copolymer and random copolymer as well. Okay, where in block copolymer you have block of A followed by block of B. Okay, large block of A followed by large block of B. In alternating you have alternate A and B, and in random you don't have any specific kind of an arrangement. Okay. Okay, now let's go on to question number 7. Changes in properties due to subsegmental relaxation are dash compared to that of changes due to alpha transition. Is it higher, or is it lower, or is it same level, or is it none of the above?
Is it lower?
Okay, why do you
B,
say so?
because it is subsegmental relaxation, no? Alpha transition is glass transition temperature,
Okay,
and below that it will be subsegmental motions. So that will be lower temperature, lower side, no?
yeah. Okay, you're right. You're perfect. It is lower. So the changes in properties due to subsegmental relaxation will be less compared to that of changes in properties due to the alpha transition. Alpha transition is nothing but your glass transition. So as you can see in this plot is again taken from the lectures only. So you could see there is a steep change in property after your glass transition, whereas the slope, is comparatively lesser when you go for a beta or gamma transition, right? You're able to see it. Here there is a steep change in the slope. Others you're able to understand, right? Whereas in case of beta transition, after the alpha to beta, there is a slight very mild change, and similarly after beta to gamma also, there is a very mild change only, right? So that is why the property changes are very less compared to that of a alpha transition. Okay. Okay, sorry, this is, I think, now this is question number 8 actually. Styrene butadiene, styrene is an example of what type?
Block copolymer.
Huh?
Block copolymer, ma'am.
Okay, it's a block copolymer, but what type of block copolymer?
Tri-block copolymer.
Yes, it's a tri-block copolymer because you have styrene block followed by a butadiene and then styrene again. So this will again be repeating. Okay, this is formed by what type of polymerization?
Ionic polymerization.
Yes. Where the butadiene anions, the styrene gets connected to, right?
Yes, ma'am.
Yeah. Okay. Hydrophobic chitin is converted to hydrophilic chitosan by replacement of is it by replacing hydroxyl group to acetylamine group or acetylamine group to hydroxyl group, or is it acetylamine group to amine group or amine group to acetylamine group? What change makes it hydrophobic to hydrophilic? I mean chitin to chitosan. This is again taken from your lectures. You can say any one of these. At least from the options you can say.
And option B.
Option B, yeah. You're saying acetylamine group to hydroxyl group. Is it so? Do all of you agree? Everyone agrees? Okay. It's actually C, acetylamine to amine group. So if you just look into the structure, so here in case of cellulose, you have the hydroxyl group. Okay. Whereas in case of a chitin, you have this acetylamine group. Okay. Cellulose, it is made up of glucose, right? Glucose units. You all know that, right? Whereas in case of a chitin, it is N-glucose acetylamine. And when it goes to chitosan, it becomes N-glucose amine. So acetylamine group, that is NHCOCH3. So COCH3 makes it hydrophobic. Right? Are you all there? Hello?
Yes, ma'am.
Yes,
Okay.
ma'am.
To NH3 group, it starts becoming hydrophilic. So careful, selective replacement of this acetylamine group to amine group, you can form a copolymer of chitin and chitosan, and then play with the hydrophobic and hydrophilic behavior. Okay. In case of random copolymer containing monomer M1 and M2, where M1 has the ability to crystallize when it polymerizes alone, the crystallization of M1 in copolymer is possible under the condition. What condition? Under what condition crystallization of M1 is possible in this copolymer of M1 and M2? Random copolymer of M1 and M2.
M2 will also crystalline, ma'am.
No. I'm saying okay. M2 should also be crystalline. Okay. What else? Imagine the okay. Imagine the case that M2 is not crystalline. It doesn't get kind of crystallized at all. So in that case, how to crystallize this M1?
The concentration of M1 monomer could be high.
Okay. But still, at some point, you will have this M2 disturbance, steric disturbance, right?
Yes, ma'am.
What are the other things possible? Of course, since polymers are semi-crystalline in nature, so if you increase the M1 concentration, maximum again, but one more, uh, thing you have to see is that it's a random copolymer. Because when you increase concentration of M1 too much, maybe you will end up with a block copolymer also, or a kind of grafted or something, because very minimal amount of M2, right? Because of your that reactivity ratios, right?
Yes, ma'am.
1-1 interactions will be more.
This is like Ra is equals to Rb is equals to 1. Then only random copolymer will form.
Okay. Yeah. Yes. But I'm saying if you increase the concentration too much, what happens? So your M1 will be much more. So obviously, the place where your M2 is very minimal, still you can form a random copolymer. And as you said, there is a possibility of crystallization as well. Only in that, longer range where M1 is there. And then where M2 is there, you cannot, form. So that is also a possible answer. Okay. Are you all clear?
No, ma'am.
Can you just repeat it, your question?
You are telling like M1 concentration has to be more. So is that related to that same concept? Ra is equals to Rb is equals to 1.
Ra is equal to Rb is equal to,
That is reactivity ratios.
yeah, reactivity ratio is, it is K double one. For example, R1 is, sorry, Ra is K double one by K 1 2. Right. So if they are 1 1 only, you'll be forming random copolymer, if I'm right?
Yes, yes.
Yes. Okay. Yes, you're forming random copolymer. That is fine. But I'm saying that his, he says that, if the concentration of M1 is maximum and concentration of M2 is very less, then there is a possibility of crystallization. I'm not saying his answer is perfect. Okay. You're able to get it?
Okay.
Yeah, you want still some more explanation?
Actually, what will be the answer? How we are explaining? Like we will be telling like concentration of M1 is more. Like that we have to tell
No,
condition.
we can't say anything. This is a random copolymer. There's no information given. So the crystallization is possible under, I'll say you the answer. That is the actual answer. Okay. So when you're cooling this random copolymer from a melt state, what should you do is that you should start, try demixing the, M1 and M2 should start demixing. Okay. And then the M2 should get excluded from the lamella. Then only the crystallization is possible. So in case of random copolymer and all, crystallization is, a little difficult. We can't crystallize because M2 will definitely come in between.
Correct, ma'am. Understood.
Yeah, you're fine now.
Yes, yes.
Yeah, that is what is the case. So this is the actual scenario you have to bring in. Okay, so you have to, there should be a demixing of M1 and M2, and then M2 should get excluded. Otherwise, your M2 will definitely come into the picture of, M1, and it may hinder its crystallizing ability. Okay. Okay, now let's move on to the Next question. Hope you are all clear, right? Are you all there?
Yes, ma'am.
Yeah, okay, okay. You're all clear, right?
Yes, ma'am.
Okay, fine. Now, next question is, miscibility in block copolymer is similar to that of polymer blends, where in the case of the mentioned copolymer domains are combined with dash, where the domains are dependent on dash. So, miscibility is similar whether you take a block copolymer or a polymer blend. But the difference between a block copolymer and a polymer blend is, what is the difference? So in case of block copolymer also you will be having polymer A domain and polymer B domain. Similarly, in a polymer blend also you will be having polymer A domain and polymer B domain. Okay, but there is a difference in block copolymer and then the polymer blend. What is that difference?
The repeating unit, ma'am.
Is it the repeating unit? See,
It
this
is
is
like
also
covalent bonding, madam.
yes, correct, perfect. In case of a block copolymer, they are covalently bonded, right? Whereas in case of polymer blends, there is no covalent bonding, right?
Yes, secondary interactions will be there in that one.
Yeah. Okay.
Or blend, huh?
Yeah. And the domains are dependent on what? Which is a key determining factor of the microstructure of the block copolymer. Block copolymer domains are dependent on what? Domains are dependent on the block length. So depending on the block length, the microstructural arrangement will vary. Okay. So what is the block length of polymer A and what is the block length of polymer B? That plays a vital role in determining the microstructure. Okay. You're able to get it? Others,
Yes, ma'am.
yeah. Okay, fine. Next question. Entropic contribution in case of mixing of macromolecules is minimal. Identify how from the Flory-Huggins theory of mixing of polymers A and B. So while discussing the Flory-Huggins theory, there was a discussion that the entropic contribution is exceedingly small. It was identified based on the equation. I have given you a clue. So what factor made the entropic contribution minimal? And where was it placed to say that it became minimal? You all want to think for a moment or shall I say the answer? So you all want to think for a moment or shall I say the answer? Okay. This is the answer. So if you just look into the Flory-Huggins theory equation, you have RTNC multiplied by phi A by NA and then ln of phi A plus phi B by NB ln of phi B plus chi into phi A phi B. So this is your equation where your first term actually denotes your entropic term. Okay. And here in the first term, phi A and phi B denotes the volume fraction of A and B. And this volume fraction is definitely, since it is a volume fraction, it is definitely going to be between 0 and 1, right? Whereas Na and Nb, it denotes the degree of polymerization. And you all know that degree of polymerization for polymer is large, right? So since this value is very large and this is a fractional value, this makes it the entropic term to be very small, and the entropic contribution becomes exceedingly small in case of polymer mixing. So the interaction parameter starts playing a very important role. So a minor change in interaction parameter, the miscibility can be lost in case of polymers, right? Hello, are you all there?
Yes, ma'am.
Okay. You're clear?
Yes, ma'am.
Okay. Next question. For a polymeric system of A and B having lower critical solution temperature, as we increase the temperature for the same volume fraction of A and B, the polymer system becomes miscible from partially miscible, or it becomes partially miscible from a miscible system, or it becomes it is partially miscible in both the cases, or it is miscible in both the cases. Which one is right? I will give you a clue. LCST is a clue. And you are increasing the temperature.
Miscible to partially miscible.
Miscible to partially miscible. You're saying that option B is the right answer, right? It becomes partially
No,
miscible.
no, ma'am. A become miscible from. No, sorry, opposite arm.
Yeah.
Miscible from partially miscible.
No, initial state
No,
will be
miscible to partial.
So state 1 will be miscible. As you increase the temperature, it becomes partially miscible. That is what you're saying, right?
Yes.
You are right. Because it is a lower critical solution temperature. So below lower critical solution temperature, the polymers will be miscible. And as you increase the temperature, the polymer starts becoming partially miscible. What happens in case of a upper critical solution temperature? In that case, as you increase the temperature, it becomes more and more visible. Whereas as you decrease the temperature, it starts becoming partially miscible because it is the upper critical solution temperature, right? Are you all there?
Yes, ma'am.
Okay, you are able to get the point.
Yes, ma'am.
Yeah, in case of upper critical solution, you would have got seen a bell-shaped kind of a curve. Whereas in lower critical, you would see a U type of curve. Just the ulta of that. Right? Okay. If we bring down the temperature of a polymer blend or a polymer solution suddenly, then we get a what type of decomposition happens. This is in case of a the system is having a upper critical solution temperature. In that case, what kind of decomposition happens? Someone wants to make an attempt?
Ma'am, it will become immiscible.
But what kind of decomposition happens? Starts becoming immiscible, okay?
It will be spindle.
Hmm?
Spindle decomposition.
Yes, spinodal decomposition with co-continuous phase separation. So there will be a co-continuous separation of phases. Okay, so it becomes a spinodal decomposition. Okay, that's all with the questions. Now the doubt clarification session. So there were some questions posted in the forum. So question 1 was posted by Shweta. I think she is here. So why silicone? Did you go through the answers, Shweta? You can type in the chat box if yes or no. Anyway, we just go through it. Why silicone is commonly used as a coating agent, whereas silicone is an elastomer, like rubber. What makes silicone restrict its application only in limited areas? Why not in tires? So, what is the reason? How to make it suitable for various applications also. So, this was a question posted by, you're able to understand the question, others? She's asking why is it used, though it is an elastomer, having a rubber-like properties, it is used only as a coating. It is used as a coating agent, not in kind of tire application. That is what she is asking. So, what is it restricting? So, the answer is, see, one thing is that not only the you know behavior of materials, class of materials alone decides its application. Okay. So not only the behavior, or class, what class of material, whether it is a glassy or rubbery, alone decides the material application. Okay. Uh, there are several other, restrictions that may play a role. Okay, and also if it is having rubber like also, it does not mean that you can replace everything by this material. Not only in this case, but in any case. See, we have, right, natural polymers in case of a, having properties as that of a, behaviors as that of a synthetic polymers, but still it is not replacing completely. Why? There may be some cost restrictions. There may be, the extent of property. Like this may give a particular tensile strength, but this may not give a particular tensile strength, but slightly lower, which may not suit. So several factors will play in deciding the application. So silicones are actually very expensive materials. That is one of the major reasons. Okay. Okay, you're clear. I hope all of you are clear. It's a costly material, but again, it's not just restricted to coating agent. A lot of applications are there with silicone as well. If you go through the silicone literatures, okay, but not all, in all places it can replace a rubber. There are several other factors that can play a role. Okay, next question was, this was posted by Udaya. Udaya, did you go through the answer?
Yes, ma'am.
Yeah, why not alternating copolymer could be a homopolymer, as it contains same repeating unit throughout the chain. This is your question, right? This question you would have asked based on this condensation polymers, right? Like PET.
Yes, ma'am.
Yeah. So this is quite different from, alternating copolymer is quite different from your condensation polymer. Because in case of condensation polymer, for example, in PET, right? Ethylene glycol and terephthalic acid. So individually, they may not be able to form a polymer. Whereas in case of alternating copolymer, each individual polymer, both polymer A and B, in any case you take, they will have their own capability of forming a polymer of their own, right? For example, polypropylene and polyethylene, right? So that is what is the answer for this. Hope you are clear. I think you would have got confused with that, condensation polymer, right? Polymerization, forming of PET and all, right?
Yes, ma'am.
Yeah. Now hope you are clear, right? Okay. Now third question again was posted by Shweta. Whether orientation of fibers or any particles in polymeric system is controllable. If so, how? Yes, definitely orientation is controllable. Okay. So orientation is affected by flow and deformation. So during the flow and deformation, obviously you can, alter the orientation, and you can align the fibers in the direction of flow by shearing action. So it is definitely controllable, but the extent of controllability, again, it comes, based on the optimization of process parameters and everything. A lot of things comes into picture. Okay, and as you asked, shearing action, it helps in orientation in flow direction. Okay, uh, that's all for today's session. So hope you all understood the session content, right? Any other feedback you have? Anything you want to ask? Any other doubts you have for the week's content? Any other doubts?
Ma'am, can you refer any book like in presentation? No, sir will be telling to read some more things. You can go and read like so the same content of slide which is available in any book in elaborated form. There we can go and read.
See, I think in your course content page itself, a lot of books sir has mentioned. I remember. I forgot the names, but it is mentioned, and in fact, in every lecture, he has mentioned what are the references he is taking from. Okay, for example, your sustainability has taken from the states in environment. He has taken from two different papers. The contents, so you can go through those papers. So you can download the lecture contents as well. uh, you're all able to download the lecture contents as well, right? There's
Yes, yes.
a one called lecture notes where you can download and you can see almost in every lecture you would have given references wherever he has taken from. Even otherwise in course content he has mentioned what are the books. So if you just go through those things, you'll get much more idea. Okay, fine.
Okay, fine.
Okay, fine. Yeah, you're satisfied or not?
Actually, I was looking for some basic book because this much book we I don't know here. I'm
Okay,
working also, so I
okay,
thought some
okay.
basic book or some basic guidelines are there, so we can go
Okay,
through it
okay.
that
No.
only.
In the course content, what are the major, books you can, those are all basic books only, whatever he has mentioned. Okay, those are all basic books only. Whereas in the lecture content, every reference is, that may be references to some papers or something. So that is the additional reading. But these basic books, whatever he has mentioned in the course page, that will be very useful. Those are all basic books only. Okay?
Okay, okay,
Yeah. Go through those books. That will be, uh, it will be very useful. Okay, uh, hope the session was fine. You were all able to understand. Any other doubts you have? If no other doubts, we can formally close the session. I don't think any of you have any doubts. Okay, let's meet on Saturday. Okay, for the next interactive session. Hereafter, it will be only on Saturdays. Only this time it's on Tuesday. Okay, Saturday 4 to 5 p.m. The same link. Okay, thank you all.